Go.
Okay. In order to understand the sliding filament model, we need to first go over the structural organization of a sarcomere and some of its key components. So we're going to start with sarcomere structure. It's composed of, well, the whole thing could be considered a myofibril, and then individual components of it are myofilaments, so thick and thin. They're composed of actin and myosin. So we're going to start by drawing in our Z-lines. So we're going to make our Z-lines red. And then we obviously are going to have our M-line in the middle. And these are different because it has to do with like what attaches to them. So from the M-line, we're only going to have thick filaments attaching. So we'll do our thick ones, we'll do them in black. So we have thick filaments coming off of it. Thick filaments are made up of myosin. On the other hand, when we look at our Z-lines, we're going to have thin filaments coming off of them. Thin filaments are going to be made up of myosin. So what happens when we have muscle contraction is that these things are actually going to be sliding towards each other. Nothing shrinks, it's just they come closer together. Everything comes closer to the Z-lines. That's how muscle contraction occurs. So we're going to look at this on a more molecular level and look at like how calcium and troponin, trypamycin plays a role. So we're going to erase this. So what I just did there, that would have been like a neutral stage because nothing, like obviously nothing was contracted. There was still space between everything. Okay. So now we're going to do, I'm just going to label a few things. We're going to do troponin is going to be in red. Trypamycin we'll make green. So basically what's going to happen is the interaction is going to occur between the thick and thin filaments. And that's what we're going to see going on here. And they're going to make a cross bridge and everything. It's going to be pretty cool. And I guess we'll just do black ATP because we know we need that. So again, we're going to have, this is our thin filament. So yeah, this is our thick filament. So the reason that this is basically like considered thick is because myosin is a globular protein. So obviously being a globular protein, we're going to see like globular heads coming off of it, like this. And so actually these heads are going to form cross bridges with the thin filament. And then when they move, that's what's going to allow, or essentially a power stroke occurs. And when they're in that high energy configuration, that's what's going to allow muscle contraction to occur. So in order for this to happen, we obviously are going to need to be stimulated. So this is something from the side, but there's obviously going to be a neuromuscular junction. And then from that, essentially in the sarcoplasmic reticulum is when calcium is going to come in. And calcium is going to initiate the troponin to change shape, which allows troponin is going to change shape. So basically it's going to go from blocking something that's going to be, like the shape's going to be altered, and then this is going to allow tropomyosin to move. So when this changes shape, it's going to allow tropomyosin to move from its original position to like a slightly different one, so like from there to there, for example, and then that's going to open up myosin binding sites, right? So once these are now exposed, now only and then can these myosin heads bind. That's what essentially is going to regulate muscle contraction. So now what we're seeing here is this combines, we formed cross bridges, and then once we have these cross bridges, we're going to actually see a power stroke occurring. So this is like standard, they're going to kind of be more like this. So this is going to yank the muscle basically, or not the muscle, yank the thin filament closer to the Z-line. It's going to pull everything closer, allowing the muscle to contract, our sliding filament model to occur. Now to break this, this is where ATP would come in, and ATP is going to break that bond, and then everything's going to slide back into a normal position.